Welcome back everyone to another video on solving physics problems. Today we're going to look at a new problem called leaning ladder, and it's classified as difficult according to the A-level syllabus. And today I'm going to go through this problem from a novel point of view, so I haven't seen this problem before. So I'll be going through as if, you know, I don't know the answer to this problem. So let's start from scratch. So the question states, a uniform ladder of mass m and length l leans against a frictionless wall at an angle theta to the horizontal with its bottom resting on a rough surface with a coefficient of friction mu. If theta is equal to 30 degrees, what is the minimum value of mu such that the ladder does not slip? So this is definitely a statics question. And how you go about this, first draw a diagram illustrating the question. So a uniform ladder of mass m and length l leans against a frictionless wall. So first what we do is draw the ground like this, and then draw a wall 90 degrees. Oops. So this is a wall. And then there's a ladder leaning against it. As such. So we know that the mass here exerts a mass of mg, and it has a length of l. And an angle of theta to the horizontal with its bottom resting on rough surface with coefficient of friction mu. So here what we do is we need to label a free body diagram. And so the two forces that are not yet present in this free body diagram are the normal forces acting on the vertical wall away from the vertical wall, F, let's say N1, just to make it clear, N1, and another normal force, which is actually, it might be better to say this is NY and say that this is NX, because it acts in the x-axis, which is horizontal, and y acts in the vertical direction. So essentially, what we have here is theta here is 30 degrees were provided, and we're asked to find mu min, the minimum value of mu, such that the ladder does not slip. And what this would mean is that if it does not slip, the forces within the system are all balanced. So what we need to do is really balance the forces, right? Oh yeah, I forgot a very important force that's present in the diagram is the frictional force. Frictional force that's pulling the ladder towards the wall. Let's say Ff as the frictional force. So that's very important. Without the frictional force, there would not be any, the ladder would not be static, basically. So what we can do here, I think, is analyze the situation. So use torques. I'm going to go with the torques method. What this means is essentially the torques at this specific point here must be balanced. So there is a clockwise torque, clockwise and anti-clockwise, and those two moments must be balanced. So the clockwise torque is obviously provided by two forces. One is the weight force and one is the frictional force. So the weight force is mg times L cos theta, half L cos theta, plus the moment provided by the frictional force, which is FF times L sine theta, and the anti-clockwise torque is provided by the normal reaction force Ny, so that would be Ny times L sine theta, and so if you want to find what mu is, okay, so let's simplify things down a bit. So the clockwise force is mg L over 2 times cos 30 degrees, and cos 30 degrees is √3 over 2, plus FF. FF is the friction force, which is also equal, this is also equal to mu times Ny, so we can say what mu Ny, L times sine theta, which is half, is equal to Ny times L times sine theta, which is also half. So now what we don't know is Ny. We want to find what Ny is. And we know that Ny is the normal force at that point. So let's think about how you can find Ny in this case. It's quite difficult, I understand. But we should be able to find something, obviously. Oh yeah, there's also a frictional force, I think, pulling it up in that direction. So we don't know what Ny is in this situation, but we do know is okay. Okay, so essentially what so are we going to say that Ny is equal to mg? I'm suspecting that because so this is what I'm thinking right now. If there's no frictional force up here, if there's no frictional force here, then the vertical forces must balance each other, which means mg is equal to Ny, right? The vertical normal force, that's obviously going to be equal, but yeah, that validates my hypothesis, because it says, look, it says the ladder leans against a frictionless wall. So what that means is, if it is frictionless, there would not be friction force acting upwards on the contact between the ladder and the vertical wall. What that means is, therefore, Ny, the normal force at the point of contact between the ladder and the horizontal surface, must be equal to mg. And so from here we can essentially cancel out mg and get L times √3 over 4 plus mu L over 2 is equal to L over 2. And L's cancel each other out. So we have mu over 2 is equal to half minus √3 over 4 times by 2. On both sides you get mu is equal to 1 minus √3 over 2. And so that's equal to 2 minus √3. And we'll see if that's the correct answer based on the choices below. I don't think that is the right answer, because it's not present in any of the answer choices. in the question. So I have to revisit, see where it has gone wrong, and hopefully go from there. So this, we're essentially using the fact that taking the torques at this point balances out. So let's revise. So we've got the clockwise torque from the weight down here. So the force is mg, and the distance we're taking is half of L times cosine of theta. I think I used a different color. I think this is correct. And then the frictional force here timesing the distance, friction force timesing the distance here, which is L times sine of theta, which is correct. And the anticlockwise torque is from Ny, the vertical normal force, times by the distance L cos theta, which is also correct. And let's have a look here. So theta is equal to 30 degrees. So cosine of 30 degrees is root 3 over 2, which is correct. This is f of f. The frictional force is mu of normal force, which is also correct, I believe. And this is also correct. So the mg's will cancel each other out. So root 3 over 4, that's correct. Mu L over 2, that's correct. L over 2, that's correct. Wait, so essentially, let's read the question again. Mass m and length L leans against a frictionless wall at an angle theta to the horizontal, with its bottom resting on a rough surface. So yeah, half mu is equal to half minus. Yes, it should be this, but I'm not sure. Because it seems like all the steps are correct. Let's have a think again. So yeah. So I think the torques are equal. Yeah, I think just based on this, the torques are obviously equal. Perhaps another way to think about it is taking the midpoint here as the torque. So what you can do here is basically say, well, ny times the L over 2 cos theta. Oh wait, I see where I went wrong. Wait a minute. So the torque here, I think that's the issue that I'm having. Should be L. Wait a minute. This should be cosine of theta, because essentially you're taking the distance as this, and this is L cos theta. So this is wrong. So this should be root 3 over 2, and simplified, this would be root 3 over 2, and mu over 2 would therefore be equal to root 3 over 4, I think. and so the mu would have to be equal to root 3 over 2. I think that is the answer, root 3 over 2, which is in fact the correct answer. So what I've learnt from doing this question is do look out for errors, and they can be quite hard to spot, especially with the fact that I ticked this box first time I was reviewing, which was pretty shambles, considering I'm not too bad at maths and physics. This should be cosine of theta instead of sine of theta, because the moment you're taking is that the force times the distance that's perpendicular to the force, which is L cos theta, not L sine theta.